Here we go. Now we're all ready to go here. Okay, here's the first idea. We're going to talk about how to find vertical asymptotes for rational functions. So we have this rational function, r of x equals 1 over x plus 2 quantity all squared. So what does this graph look like? What parent graph does this represent? What is it? Yeah, the tree trunk. So let's go ahead and draw the basic tree trunk on here just really quickly. So we know the tree trunk will have negative 1, 1, and 1, 1. So this is the basic function r of x equals 1 over x squared, right? That's the basic one. Now, what does that plus 2 do underneath our inside our function but on the denominator? What's that going to do? Shift it which way? To the left 2 units, right? So take each dot, all right, and move it 2 units to the left, 1, 2. And take this dot, move it 1, 2, 2 units to the left. But you also have to move the asymptote 2 units to the left as well. Now, there are 2 asymptotes in this general function. So it'll look like this over here, and then it'll look like that over there. So if we're looking for where the vertical asymptote is, what do you notice? Where is the vertical asymptote? Yeah, what's the equation for the vertical asymptote? X equals negative 2, right? So the question is, how do we find that without having to use the graph and use algebra? So to find, that's what we're going to do. To find the vertical asymptote, I'm going to use VA for that. We're going to set our q of x, the denominator, equal to 0, and solve. So that's going to be x plus 2 quantity squared equals 0, and then we're going to solve this. Yeah, thanks a lot. High CPU usage. X plus 2 equals, if we square both sides, I get, or square root both sides, I get 0 out of that. So then x must equal negative 2. So notice the algebra, right? The algebra matches up with the picture of moving my graph 2 units over to the left. So the horizontal, finding the vertical asymptotes for any rational function, we're going to set q of x. I'm talking to myself here. Don't worry about it. All right. How do you find vertical asymptote technique that you use? What's the strategy that you use? Sum it up for me. What do you do? It's over here in this circle over here. What do you do? Yeah, you set the q of x equal to 0 and you solve. All right. So to find a vertical asymptote, that might be a great question that you revise your notes with. How do you find vertical asymptotes to rational functions? That might be the question you ask yourself. All right. We're going to move on to how do you find horizontal asymptotes? Already, yep. How do you find horizontal asymptotes? For a rational function. That's a pretty good guess. Okay. Well, I'm going to start you off with a rule here. Okay, and here's the rule it's going to be. And we're going to introduce a term that's called proper. And it's an if-then statement. If some stuff, then some other stuff. You guys are familiar with if-then statements, correct? Yeah. Okay. So, if r of x is going to stand for your rational function. If your rational function is what we call proper, and we introduced this term the other day, we're going to dive into it a little bit more today. If your rational function is proper, then y equals 0, also known as the x-axis, is guaranteed to be your horizontal asymptote. I'm going to use HA for horizontal asymptote. So this is a equals 0, the horizontal x-axis is a horizontal asymptote. It's a great question, great segue. What exactly does proper mean? Okay, proper. Proper means the degree on your rational function. Okay, the degree of your rational function, where r of x equals p of x over q of x, right? The degree of p of x is less than the degree of q of x. So kind of like a proper fraction, right? A proper fraction would be something like 2/3. That's a proper fraction. The number on the top is smaller than the number on the bottom. You agree with that part? Deg means degree. DEG is short for degree. So proper means that the degree of your rational function, p of x over q of x, the degree of p of x is smaller than the degree of q of x. So let me give you an example of exactly what I mean by that. So here's a rational function, r of x equals 3 over x plus 1. And here's another example. R of x is equal to 3x over x squared plus 17. Okay, let me extend this line a little bit here. Let's examine this first one here. What is the degree of p of x in that example there? What's the degree going to be? No, not 3. Have we forgot what degree is? No, not 1 either. 0. This is like 3x to the 0 power, so the degree is 0. What's the degree of the bottom? This is like x to the first power. Do you guys see that? Hello? Wake up. Yeah, so that means 0 is definitely less than 1. 0 is less than 1, therefore this is a proper rational function. You guys with me on this? Okay, yeah? Hello? Okay, good. Let's look at example 2. What is the degree of p of x? What's the degree? 1. Very good. This is like x to the first power. What is the degree of q of x? 2. This is like x to the second power. There they are. 1 is less than 2, therefore this is proper. You guys feel me on this so far? Now, if these are proper rational functions, you tell me, where is the horizontal asymptote? What's the theorem say? The x-axis. Awesome. So this leads us right into the next segment. Okay, well, we know how to find vertical asymptotes for rational functions. We set the denominator equal to 0 and we solve it the same as the domain. We know that if our rational function is proper, then the horizontal asymptote is guaranteed to be what, everybody? If it's proper, it's guaranteed to be what? X-axis. X-axis, good. And how do you know if a rational function is proper? I'm sure somewhere in all that muddled mess was the right answer. Yeah. The degree of the top is smaller than the degree of the bottom. So that begs the question then, okay, what if your rational function is not proper? Okay. This gets split off into 2 cases. Okay, so this is going to be case number 1 and case number 2. Case 2. This is 2 cases. So let's say your r of x, again, is equal to p of x over q of x. All right, and in this one, r of x is equal to p of x over q of x. Okay? In case number 1, the degree of p of x is actually going to equal the degree of q of x. Okay? The degrees are going to be equal. In this case, case number 2, the degree of p of x is going to be greater than the degree of q of x. You guys with me so far? Okay, so remember, if the degree of the top is smaller than the degree on the bottom, then that's called proper, and that defaults to y equals 0. If it's not proper, then we have 2 cases. Either the degree on the top is equal to the degree on the bottom. An example of that would look like this. I give you a rational function that says, what if my r of x is equal to 3x plus 5, all divided by 2x plus 7, okay? Take a look at the degrees there. Notice the degrees are equal. You guys see that? The degree of p of x is 1. The degree of q of x is also 1. You guys understand so far? Good. Now, let me give you an example of this one. Case number 2 where the degree is larger than the degree on the bottom. So that would look something like this. 20x squared plus 3x all divided by 5x. All right? Do you see the difference between these 2 cases here? I know Rebecca does. Anybody else see the difference in the 2 cases? Okay. Yeah, exactly. The degree here is a 1. The degree there is a 1. The degree here is a 2. The degree here is a 1. So on the left-hand side, case number 1, we see that the degrees are equal. On the right-hand side, case number 2, the degree on the top is larger than the degree on the bottom. You guys good so far? Case number 1 is far easier than case number 2. Remember, our whole goal is we're looking for horizontal asymptotes. The horizontal asymptote in this case is the equation y equals 3 halves. What? How did I do that so fast? Who sees it? You got it. It's when the degrees are equal, it's the coolest thing in the world. This right here is your horizontal asymptote. How sweet is that? I don't think you guys recognize the magnitude of the sweetness that's just happened here. There's this amazingly sweet.
That is prime sweet.
I know it is. Okay, I'm gonna prove this to you right now. Okay, so go ahead, write that down. And I'm gonna bust open fluid math, and I'm gonna show you exactly how this works. Someone remember that rational function? Okay. You guys remember it? Okay, good. It was y equals what was it? 3x plus 5 all over 2x plus 7. Is that true? Does that look good? Yeah? Okay, good. I'm going to graph this line right here. Okay, this is a rational function. And there it is right there. Okay. So here's my rational function. And I'm looking for the horizontal asymptote, right? Now notice the horizontal asymptote is not the x-axis because it's not proper, right? Watch this. I'm going to graph the line y equals 3 halves because that's the coefficient of my highest degree terms, the 3 divided by 2, right? Watch this. Oh, snap. Look, there it is. How sick is that?
Pretty sick.
I am not feeling you guys. This is so amazing. This is the most amazing thing since...
We've already been through this. It's prime sweetness.
Prime sweetness. Yeah, you got it. Okay, good. Okay. All right, good. Let's go back over to our notes then. All right. You tell me. I'm going to give you another one really quick here. Okay, you tell me. Here's a rational function. R of x is equal to 2x squared plus 5x all over 7x squared plus 6x. You tell me, where is the horizontal asymptote? The equation y equals what? 2/7. You guys got it. That's pretty sick, right? Okay, now, like I said, case number 1, much easier than case number 2. Okay, let's take a look at case number 2. In case number 2, we notice that the degree of the top is larger than the degree of the bottom. But how much larger? Now, this is the key to understanding this. How much larger is it? Yeah. So can I make 4 times? No, not 4 times. Okay, I'm going to do extended box. Okay, sorry. Because I need more room to talk about this. Don't hate me. Extended box. I'm going to rewrite that function. R of x equals, it was 20x to the second, right? Plus 3x, all divided by 5x. Okay, I'm going to make a little note over here, special note. What is the degree of q of x? The degree of this one. What's the degree of that one? 2. You guys, right? That's the degree of equal to 2. What is the degree of q of x on the bottom here? 1. Okay, that's a degree. This is a degree of 1. And we already know the degree on top is larger than the degree on the bottom, but by how much? That's my question. What's the difference between the degrees? 1. There you go. So that's the note. You can only find an oblique asymptote if the degree of p of x is larger than the degree of q of x by 1. Super important. Okay? You can only find an oblique asymptote, and yes, I am talking about oblique. Okay? You can only find an oblique asymptote if the degree on top is larger than the degree on the bottom by 1. Okay? If the degree on top is more than 1, if it's exactly 2, then you get a quadratic asymptote, which is awesome, which we don't talk about in this class. That's called calculus. Okay? So, and the way that you get it, ladies and gentlemen, is by long division. There it is. There's my class. You get it by long division. But it's actually like long division, like easy style. Because after all, you're just looking for a line, right? All right, so here we go. We're going to find the oblique asymptote here. Here you go. Ready? It's going to be 4x on top, 4x squared. No, sorry, excuse me. Excuse me. 20x squared plus 3x all divided by 5x. This is easy. And the reason it's easy is because you're just looking for y equals mx plus b. As soon as you have that, you can stop. Because you're looking for a line, after all, correct? Right? An oblique asymptote is just a line. Yeah? So here we go. Do it with me. How many times does 5x go into 20x squared? 4x. Look, there's the mx part. Oh, that was hard. All right, so 4x times 5x is 20x squared. We're going to subtract this stuff. 0 by design. Bring down the what? 3x. Correct? How many times does 5x go into 3x? Yes, 3/5 times. And you're done. There you go. Therefore, the oblique asymptote is equal to y equals 4x plus 3/5. There you go. That was nice, huh? Okay, let's turn this back on. So we just graphed our rational function, which is 20x squared plus 3x over 5x, and we're looking for an oblique asymptote. There's no horizontal asymptote because the degree on top is larger. We know that when x is equal to 0, we're going to have a hole because you're not allowed to divide by 0. That's why there's a hole right here. When x is equal to 0, there's a hole in the graph. Kind of interesting, right? But we're interested in this oblique asymptote, and through long division, we found that the oblique asymptote was 4x plus 3/5. Is that right? Yeah. Okay. That does not look like 3/5. Let's try this again. 3/5. Does that look good? I did it right? So when I put this one onto the graph, you'll notice that we find exactly that oblique asymptote, and as far as you go out, that line is going to behave more and more just like that.